morning, everyone. So let's get started with today's talk. So it's our great pleasure to have invite Dr. Bedros Afeyan to give our diffusion talk view from the top. Okay, so Dr. Bedros Afeyan is a plasma physicist specializing in laser plasma instability physics and associated control, kinetics, fluid modeling, analysis, laser innovation path to success. And he's been doing a lot of research on that. So Dr. Afeyan's PhD is from University of Rochester on theoretical plasma physics. Now today, let's learn about the right things to do for IFE related research. And thank you very much.
Thank you. Can you hear me? Great. I once took a plasma physics class taught by Bill Crewer at Livermore, what's called UC Davis Livermore. And he would come in, and some of us would be from Livermore, but this is a Davis class, so this is 30 years ago. So very fancy video system tied to Davis, which is 90 miles away. And he'd come in and say, "Can you hear me at Davis?" And somebody would, "Yes." And we'd never hear from them again. So I had a theory that they designated one guy to show up and just say yes, and they went off and did their own thing because they never asked questions or anything else. So I'm glad you're here. I don't know about the people on Zoom, but I'm glad you can hear me. So I want to tell you about LPI, laser plasma instability, and how to control them, and the stud pulse program, which is related to that for inertial fusion energy. You must have heard of inertial fusion energy. It's in the news now. Billions of dollars are being spent on it, and all sorts of claims are being made. There's also this other lesser form called magnetic fusion. You might have heard of that, and they're making noise too. But of course they don't even have ignition. So it's a hopeful field. It's a field where hope precedes facts, and that's a very good thing, as long as it's bounded. So I have many co-authors, which some are mentioned here. I'm going to show work. I'll hope to remember when I show particular work that was done with people in the past that I make reference to them and acknowledge their contributions. So here, there's Jeff Hittinger, Young-Soo Choi, and Tony Chang from Livermore, who work on the ML aspects of this and numerical aspects with me. And then Tommy Hosmer, who's a student here, who also is a second-year student. So he's been in a whirlwind working on all this stuff and trying to make a contribution, which he's been very good at. He's a very conscientious guy. Okay, I think, so ARPA-E Open is the current sponsor for some of the work I'll show. Many of the works to catch you up with this field will be years ago. So they were funded by DOE's program on HEDLP, as well as Air Force Office of Scientific Research. All right, so this is the what is LPI part of the talk. So let me tell you what a whole ROM is. So you can think of LPI as something that happens good in a whole ROM. So a whole ROM, I remember John Lindell was giving a talk at a AAAS meeting in Washington once, and by the time he was done talking about the target, one of the questions he's got is this the size of a basketball? And so I don't want to fail at that. This is a little thing like this, in case you think, just because it's drawn like that doesn't mean that it's a big thing. It's tiny. This is less than a centimeter, so the whole thing is pretty small. But it's a complicated object in the sense that there's many different kinds of materials that can fit in here, must fit in here. There's a gas fill, there's gold, there's CH, there's ablators. There's just a simple laser plasma instability experiment. There, one target made a one thing, and then you shoot it with a laser, and that's already very bad. This is a lot more than that, right? And then, just so you don't misunderstand, there's 192 beams coming in, half of them from here and half of them from there. And 2/3 and 1/3 of those are going in somewhere here versus there, and there's 4 cones of beams. So it's complicated. And so here's a little bit of a depiction of that, of the beams coming in and where they go in and what they do. And so the various processes that can happen and where they would happen is indicated in this plot. I'm just trying to tell you that there's a lot of things you got to worry about. This is not a cartoon picture of this target. All right, so one of the principal points I try to make in the abstract, how many of you read the abstract? Anybody? Okay, so I figured, you know, you put people to sleep when you talk, so I was give them something to read first, so some message gets passed, even if you don't pay attention here, or worry about your next exam or something. So the message is, control has never been the operating principle by which this field has evolved. Plasma physics is a new branch of science. It, you know, the collective behavior of charged particles is a complicated, you know, classical many-body theory is a very complicated field, delegated to statistical mechanics, which usually works off toy problems. So this is not a toy problem. Non-equilibrium statistical mechanics is a very serious problem. And there's a lot to be gained there. And in that field, you can have instabilities, which is studied by other people, not statistical mechanicians. That's studied by people who work with nonlinear optics. And they try to make a simple model of the medium, typically, because they're more interested by what's happening to the photons. Punchline is the difficulty of this field is that there's no real experts in it. There are either experts who know about plasmas or they're experts who know about lasers. And there's nobody who knows both, which is because of the education system we're in. I mean, it's natural. There's nothing surprising about that. But unfortunately, that's what you need. And that's permeates all of inertial fusion. So in every step of the way, because it's multidisciplinary, there's no experts in all of it. So depending on who's calling the shots, it gets pulled in one direction at the expense of other directions. And so the field has been tumbling around for 60 years. And the way to overcome that, and maybe ML, here's a punchline, might be one of the ways in which what you don't know gets incorporated anyway. And so, you know, make experts out of non-experts. Supersede them. So, but I'm only going to talk about LPI. So this is just take my word for it. This is exemplary. I could have taken any other aspect of an implosion and I could have made the same points. That if you understand the mass, you don't understand the conductivity, you don't understand conductivity, you don't understand the thermal properties, you know, something's being kludged every day in laser fusion. There's a quote for you. And getting rid of all those kludges is the job of academics, right? It's not the job of people trying to make more neutrons. So a prime example is LPI. And so we want to tame these instabilities. Doesn't mean I want to get rid of them. I want to control them. I want to make them big or small whenever I want at my instigation. That's the goal. And so we want to do very fancy things to do that. And we want to push the boundaries of smart computing so that even our codes can do something better. If you know what these words mean, good for you. And yeah, so this is sort of a wish list for experts. The rest of it is not for experts. What's coming up? I mean, not as bad anyway. But in case you were like a big expert in this field, this is what I'm saying. Okay, why isn't it moving forward? Okay. So here's a summary of the stud pulse program for IFE. Is there any way to get rid of that thing? I don't have it here. Excuse me. Yeah. Well, what is that?
Just select out of it. The thread line thing. Just X with X.
Yeah, but I don't have it here. Oh, I can do it here. Oh,
Yeah.
okay, let's do that. Thank you. Hope it doesn't try to
No,
update my
not
system. Yeah, but now I have to hear here. I don't wanna do it.
Give me a second.
So, what are stud pulses? So I've given you enough background. So I'm claiming that you can control LPI using stud pulses. So let's get out of acronym mode. LPI is laser plasma instability. Stud pulses stands for spike trains of uneven duration and delay. So you don't want to just turn the laser on and hope that these things don't happen. That's been what the field did for a very long time. Okay? In other words, the laser people designed the laser, they designed the pulse, mostly done by hydrodynamicists about the implosion shock physics. And then they turn around to the plasma physicists and say, why don't you get rid of these instabilities? And so the answer is, you pick the target, you pick the laser. What am I supposed to do? Do some kind of Indian dance around this thing so this thing goes away? What am I supposed to do? There's no knobs. It's done.
Bedros, before, maybe go back to 2 slides to your picture, just so we get sort of mentally oriented. When you talk about the laser plasma instability, are we talking about the development, temporal development of spatial instability, or are we pumping the beams into a different frequency by forward mixing? What type? Give us a little.
No problem. No problem.
What is going on?
Sure. So this means you guys didn't go and Google the words that I had in the. Okay. So I'll be your Google now. Thanks. So lasers come in, right? Half of 192 of them, another one there. And first, when they get into the whole ROM, there's a hole here called an LEH, because Livermore people can't live without TLAs, which stands for 3-letter acronym. And they cross here, okay? And so they can interact right there at the LEH, light entrance hole. And that's an SBS process, stimulated Brillouin scattering process, that's Googleable. And then, but they like calling it CBET, so for cross-beam energy transfer. So that means that energy goes from one cone to another cone. And so this, multiple millions of dollars were spent. I don't want to tell you how much, $27 million were spent in trying to design a ratio of inner and outer cones that's going to tell you what the right way of doing this is. And it's all nonsense. It turned out that they used cross-beam energy transfer to have 50-50. They designed it to be 2/3, 1/3. That was the only thing that was going to work, blah, 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 blah. And once they shot it, they realized, oh my God, most of it is going one place because of this transfer. Let's try to reverse that. And then they settled for 50-50, which is obviously not optimal. If it were, they wouldn't be selling 1/3, 2/3. So that's the kind of embarrassment that happens when you just have a lot of hubris, which fusion is full of. Now, once you get these beams in, then they can backscatter light through these 3-wave interactions, which is to say 2 light waves and some plasma mode. If the plasma mode is a plasma wave, what's called an electron plasma wave, then it's called stimulated Raman scattering. And if it's an ion acoustic wave, then it's stimulated Brillouin scattering. And Brillouin is not Berloin. I always like to say there's no loins involved. Okay, the guy's name is Brillouin, French famous physicist, one of the founders of quantum mechanics. So what these things do, what SRS does as well, and then there's 2 plasmon decay if you get the quarter critical density. Critical density is a density of, how many people here are taking a plasma class? Good, a minority. So if you hit laser at a plasma, as density is going up in the plasma, why is that? Because at some point it was a solid. So whatever you did to it to ablate it, right? There's a place at which it's going to get pretty dense. And so there's a place at which it bounces back, no matter what the frequency of the light is. It's further and further dense if it's X-rays than if it's, CO2 lasers. But anyway, there's always a density at which the plasma frequency, the local oscillation of electrons against the non-moving ion background, is the same as the frequency at which you're coming in with the light. And you can't go past that. And quarter critical is a quarter of that, and that's where 2 plasmon decay happens. This is a killer instability called the silent killer because it only makes plasma waves. So it's not easy to see lights coming out. Oh my God, I did something wrong. I like to say there's no market for $4 billion mirrors. Okay, so this becomes a $4 billion mirror when Raman scattering, for instance, or Brillouin scattering reflect the light right back out. Okay, but Raman is much more sinister than just reflecting that's the nice thing about Brillouin, is that the frequency of the acoustic wave is so small compared to the light that due to a fundamental action conservation principle, which is called Manley-Rowe relations in electrical engineering, and that's the term we use now as well. E squared over omega is conserved when these processes happen. So if one of the omegas is very small, then therefore the E of it has to be small so that this ratio is the same as a high frequency guy. And so all the light goes to all the energy goes into the scattered light wave in the case of Brillouin because the frequency ratio is 43. And while the other one, the frequency ratio is of order 1. So the energy is shared between the plasma wave and the light wave. And a plasma wave that's getting a lot of energy gets to be big. And when it's big, it accelerates electrons. I'll show examples of that in a second. Okay? It just wave breaks and spews electrons around. So if there's a lot of hot electrons, they'll come and heat this thing. Okay? Now, the whole point is to keep this cold and try to compress so that then it heats itself from the pressure. If this thing is preheated, then you can't compress it. Things that have particles that are moving around a lot aren't going to get compressed. So we try to keep this cryogenic and as cold as possible and this and that. And one little process over here, besides the $4 billion missing, market, there's also no market for preheating this thing. Makes your job harder, right? Does that answer your question?
Yep, thank you.
Thanks for giving me that prompt. All right. So what we're going to try to do, there's claims here. So I'm going to tell you what stud pulses are. It's going to be a bunch of spikes. And the program has three kind of versions of it. The one that was initially invented is this Ferrari. It's how to get rid of it for a single beam. Mercedes is to do with crossing beams, and this is all about avoiding crossing beams. So I'll just say that I don't drive a Ferrari. The experimental evidence for gross LPI anomalies is very high. And then they got really bad on NIF, right? So on NIF, about 300 to 600 kilojoules was being squandered. And then also it was going where you don't want it anyway, so it's really bad. And so you might want to compare a uniform, just a simple plane wave, to what the rest of the community touts as useful, and then this new thing. So key idea is that plasmas tend to self-organize. If you keep giving them energy, they're going to do what they want to do. And that's going to be something you don't want. Because the best way to heat up this outside in order to get pressure, in order to push the stuff in, is to have thermal distribution. You don't want to have complications. Self-organization is a very nonlinear, non-thermal thing. So if this is happening, you're not just creating some pressure to push something in, you're doing fancy things which have to do with waves interacting. Okay, so the only trick you can pull is try to fool the plasma into not forming memories. You want the plasma not to have any memory of the last time it saw a laser to the next time it sees a laser. And we're talking about sub-picosecond time scale here, okay, because the growth rate is picoseconds. So before it can grow, and then go, okay, thank you very much, now I'm going to do my own thing, you want to sort of disrupt that. So you must fool the plasma into not forming memories as with continuous pumping. If you have a continuous pump, whatever the plasma does can keep doing because it's still going to be fed energy, right? So kill this thing and don't allow it to accumulate. And so I'm going to show you. So one of the predictions of just this statement here is that if I show you time evolution, some snapshots of this thing is developing in a situation where memory is building, you should see much more complicated things than when I do what I do, and magically it won't be complicated anymore. It'll be democratized gain. It'll look like a little bit is happening everywhere. You agree with that? So look forward to that. That's going to be shown to you. Okay, so now the other ideas is that, so this is the best one because it came for free. I worked out the Ferrari, and then this thing I realized is also going to be true, which I wasn't trying to do at all, which is solve the cross beam problem. Okay, so if I have a bunch of beams crossing, and if they cross at the same time in the same place, they're going to interact. But because I turn my beam on and off, they don't have to interact, even if they're in the same place, because I can intersperse them. And then it's a little more complicated to explain the Mercedes program, which has to do with speckles, which we're going to see in a minute, in the data, and the speckles make some parts of the beam more energetic than others. So that's where the instabilities start. And then they can talk to each other, and then they can cause an avalanche all over the beam. That kind of sophistication can be headed off by the Mercedes program, which makes, it's exchanging leopard marks between beams so that it's a temporal smoothing process. We're mostly going to talk about Ferrari, I guess. Okay, so let me skip some stuff because now you might say, well, wait a minute. So anybody here taking the electromagnetics class? Graduate electromagnetics class? Anybody taking JDJ? Anybody know who JDJ is? Or besides my learned colleague here? You do? He was an institution in Berkeley. He was at LBNL, but he's a Canadian. That's an important thing to mention. From Montreal. But anyway, JDJ went to McGill. I'm from Montreal. But anyway, JDJ was a very good physicist who wrote a textbook on electrodynamics, which I don't like. I like Landau-Lifshitz better, so read that. But if you looked up what an electric field looks like in general, then you'd know that it has a polarization, it can have an envelope, it can have a wave number, it can have a frequency, which could be varying as a function of time, and a phase. That's it, okay? Any electromagnetic wave looks like this, let alone a laser field. So in general, I'm telling you, we're going to do something to the laser in order to control the plasma, right? So you might say, oh, wait a minute, let me sit down and see, why don't I vary the polarization? Why don't I vary the frequency or the wave number or any of these things, or the envelope? Which of those is going to be most effective? So have fun doing that. I'll tell you the answer. It's the amplitude envelope. Because that's the only way you can stop an instability instead of swapping out one instability with another instability. Because remember, while we look at three-wave interactions, there's a whole bunch of three-wave interactions going on. If I zoom in on one and try to kill it, I'm most likely going to make another one worse. And there's no way I'm going to make all of them go away unless it's a cartoon Disney World story. Okay, in other words, my model of the plasma is sub-serious. All right. So the thing that everybody thought of in the 70s was, hey, if we add bandwidth, if we don't make this just coherent, completely coherent, one frequency, that's got to make three-wave interactions less active. Yes, that's true. Is that enough to get rid of them? No. Is that something people are selling? Yes. Is that the main stream of the whole field? Yes. Add bandwidth. You'll always find an instability in some condition where you will make things better. And that's what they sell. As opposed to solving the problem, which is adapting to whatever's happening in the plasma, which you cannot know. Did you see how complicated the target was? 192 beams hit it. How are you going to know what's going on in the plasma? So the reason nobody else thought of this as a solution is because it sounds crazily complicated, which is you're supposed to solve a problem without knowing what the problem really is. So you have to have knobs by which you can learn. This is why learning is important. High rep rate is important. All that stuff that I wrote in the abstract are important because without that, this can't be done. And the field in the 60s, 70s, 80s, 90s didn't have high rep rate lasers, didn't have ML, didn't have anything. So to them, they had to come up with cartoon stories to show progress. Now it's sinful to make cartoon stories. They're still doing it because we can actually use these tools to make progress. And I'll show you that. Okay, let's move on. So what's the substantiation of this and what are the knobs that define it? So you can have some Gaussian or some Gaussian or 10 hyperbolic or whatever you want, pair of 10 hyperbolics, way of having something that goes up and comes down, looks like that. And then for each of them, each on-off pair here, right? Notice that I can define how much of it was on. That's called the duty cycle, right? 100% duty cycle will make this a flat thing. I can define so there is a nonlinear time interval over which bad things are happening in the plasma when you don't have this, when it's a continuous version. And so if you have foreknowledge of that, because you do that simulation first, and you realize what that time scale is, you can now bring that in and decide to make this on time be some fraction of that. Okay, so if I make it very much large compared to that, of course, it's not going to work because that's the same thing as a continuous pulse, which is what we're trying to defeat. So it's going to have to critically depend on this nonlinear timescale. And then, because in general, those of you like using words like R3000, the number of knobs in this problem, if each one on-off pair is designed independently, would be 3 times 3,000 dimensional space. So good luck with that. But I want to find, I'm just a physicist, so I want to find a low dimensional equivalent thing I can study, at least to start, before the ML. And so that allows me to put in some jitter to make these not the same size, not the same height. So I get to explore a little more by just playing with the jitter. Some random, fattening and thinning of these guys, on average being whatever I decided VT on is. Okay, there's another reason to do that. Picket fence is about the stupidest idea you can have, because picket fences will start other instabilities, because now you're introducing another coherent frequency into the plasma. So if you don't take nonlinearity into account, you can fall into this kind of trap of thinking, oh, look, I got rid of that three-way thing. Yeah, right, except you caused other ones. So there's really two kinds. I'm not going to bother. I'm just going to tell you about Imax fixed. All the ones I'm going to show you are the integral of this curve is the energy, right? The integral of the intensity over time is the energy. Energy is always going to be the same in everything I show you. But there's two ways to make the energy the same. You can make the pulse twice as long. The pulse width is going to be the same. That's Imax fixed stud pulses. I'm sorry, T-pulse fixed stud pulses. So I'm only going to show the pulse width is fixed stud pulses, right? I could make the top be the same, but every time I reduce this on time, I'd have to make it proportionally longer. We won't talk about that. That's much easier to deal with. So I'll show you the hard problem. T-pulse fixed. Energy is fixed. Duration of the pulse is fixed. Inside, I can do whatever I want, and I want to see what gets rid of instabilities. Fair enough? Okay. So this is a long thing, which is in the abstract. This is what I put in the abstract, of what the hell is wrong with saying that bandwidth is enough. What is the con job is that when you say bandwidth is enough, you're really limiting the space in which you can look for it to be good enough. And that is near threshold. Just when instabilities are about to go. Now, intuitively, do you think that's the worst thing? Do you think when some laminar, how many people here have taken fluid mechanics? Okay, so do you think when we go by laminarity, we get one eigenvalue, CC Lin or something, or Heisenberg, one eigenvalue goes in Poiseuille flow. Is that the problem? No. The problem is when you get the turbulence. None of this will work if you get the turbulence. Everything I'm going to show you is going to be near turbulence. Okay? So that's the simplified, non-sophisticated terminology by which I want to tell you about this. So I told you about speckle patterns. This is what lasers really look like. It's because of coherence, but I can't give an hour lecture on speckles, so you just have to look at the pictures. So this is a laser beam. It's actually two crossing laser beams, and they have places where the intensity is much higher. Do we know what the tail of that looks like? Yes. It comes from Gaussian random field theory and n dimensions. Good luck learning that language. This is the three-dimensional version, which gives you a statistical estimate of this should not be equal. This is statistical, this is an average thing. So the expectation value of the intensities larger than U decays like this. So that's, I know that's not easy to grok like in a second, but it's not my problem. So now let me give you an insight by example. Here's the laser beam, here's another laser beam, different realizations. Here's me catching its speckle pattern, here's me catching the other guy's speckle pattern. You can ask how many of them are on top of each other. Two random picks from a Gaussian random field. So what's your intuition? A lot of them or just a few of them? Well, I'd have nothing to say if it was a lot of them, right? Because I'm telling you that you got to do things, actions, which stop it from accumulating memory. One of which is randomizing the speckle patterns. So the answer is good news. It's a few of them. So this actually is doing the work of actually catching its hotspots and then put them on top of each other and see how much they overlap, and they don't. So that punchline will come in a second. Okay, so there's some statistical things here about what you can say about their heights and widths, but let's just skip all that, all right? So here now is an actual model of LPI. So you have a pump wave, which is called A naught, and it's got this form, and it's coupled to the plasma wave, plasma mode, whatever it is, and the scatter light wave. And the scatter light wave, this is its propagator, and then nonlinear propagator, and then because it's got A naught squared in it, and then it's also coupled to the other wave. So this is a three-wave interaction where two waves come together and generate the third wave, and the third wave talks to one of them and generates this wave. So this is a thing that can just grow. Okay? So this is a solvable model for LPI analytically, non-linearly, and from it you learn that there are three length scales that matter. And this kind of going to make sense. Remember those little white things that I was showing you? Those are called hotspots or speckles. And a hotspot is a length. So that length is going to come in, obviously. If I make the F number of the lens very long, this thing is going to be very long. If I make it a fast lens, then it's going to be short. Another thing is the interaction length, which in a few pages of algebra I will flash in a second. You can calculate explicitly from a theory that I told you is analytic. And that gets you the interaction length. And the third thing, that's our thing, is how far does a beam propagate in a given on time, right? So that's the spike length. So here's the punchline. Now, whether, what those are in these formulas, and in the ones coming up, which I'm not going to dwell on, the key point is you'll learn eventually, if you stare at this long enough, that the critical, go back to statistical mechanics, the critical scaling is when the hotspot length and the interaction lengths are the same order of magnitude, right? If the interaction length is very short compared to the hotspots, you're never going to use the hotspot. So that's not a hard problem. If the interaction length is very long compared to the hotspot, you're cooked, you're finished, because it's the same thing as just being on all the time. So the critical case is when these are the same size. And then the question is, how big is this compared to them? Okay? So it looks like three lengths, but in reality, it's just two lengths, because the most critical case is when the interaction length is the same as the hotspot. Because that's how much you could have grown if you don't turn the laser off. That's how bad it's going to be, right? Okay. I'm glad you got that, because so now, as I told you, this is what I'm not showing you, is how to get those lengths and stuff. So now you know that there's knobs that you get from this problem. So let me translate this to physics talk to you. So we'll call little l int, this ratio, which I said, think of that as 1, the interaction length divided by the hotspot length. And then there's an L snip. This is like a Moyle idea. It's when do you turn the laser off, right? So that you don't use the whole hotspot. So that's the spike length divided by the hotspot length. So the way we talk about them is that it's say a 50-10 X1 means that 50% duty cycle, 10% jitter, and I'm going to change the speckle pattern every time I turn it on and off. Kind of an extreme case. And that, in this parlance, also known as language, is 1, 1.5. Okay? So L interaction is 1, L snip is 0.5. Now, if I say 20-10 X2, then again, I'm going to assume the first two are the same, but now the second one is 1/5, or it's 20%. So where does it say quarter? Should be 1/2. No. X2 is how often every 2 spikes I turn it off, and then 20-10 should have been 1/5. So it's not a quarter, it's 1/5. You're reading wrong. Now, 30 is 1/3, correct? 60 is 60%, 80%. So that's how we call it. Now I'm going to show you pictures. So this is what those lasers in 2D look like. Remember, there's a very different scale in this direction than the other direction, right? There's a factor of 3 thing. Otherwise, I'd make it too thin and you wouldn't see anything. So as a function of time, see, it's being turned on and off, and any given speckle has a certain size, certain length, okay, a width, and a certain height. So the distribution of them, and these are various kinds of stud pulses, all right? So 50, 10, 111 looks like that. Now we're going to look at what happens in the plasma to the laser. That's this thing. This is a non-varying speckle pattern, a wrong laser. Scatter light wave, which is being amplified this way. So you can see how much worse it is here than there. And these seeded places where it all happened, those are the hotspots. And the other one is the acoustic wave memory. That's how much information is being seeded in particular places in the acoustic wave field. Okay, it's important that this slide makes sense, all right? So now I'm going to show you ways of getting rid of all of this information that's worst here in the continuous case. Because the same hotspots got hit over and over again for, you know, many, many growth times. So now I'm putting in stud pulses. So instead of seeing the original speckles, you're seeing that I'm cutting them, right? They're all being cut. And as I do, just to keep this short, notice what I can do. Look what's happening to the acoustic wave information as you go to the right and bottom. See that? Compare that to this. Oh, in fact, that's why I left the top one there. So that's an example of a bad thing on the top left. And look at how uniformized everything has gotten. Not just smaller, but also less information per square centimeter. More of that, right? A bad thing shown on the top left, a much better thing shown on the bottom right. And just look here, I've gotten rid of everything. Okay, so let me summarize what I just showed you. And here's a case of things very good, and then we go to the right, play with the knobs, and then it gets big again. There's no magic. So this is the summary slide. This is the, what we call the money shot. So this is the reflectivity of Brillouin, SBS, versus the duty cycle for various SNP rates, every spike, every second spike, fourth spike, eighth spike. What do you think happens when you make this number like 16? Well, it's like you're not snipping it at all. So you expect the curves to go right up to where RPP, SSD, the rest of the technology of the field is, here. So we picked the case which is more than 10% reflectivity to begin with, in their hands, okay? And then I'll show you here that if you can come close to the bottom left, you get 4 orders of magnitude reduction of an instability with the same energy and the same duration pulse. So here is technologically challenging to do things here, you know, but here, look how many, looking at 4 orders of magnitude. You know, factors of 2 gets you a PRL in this field. Square root of 2 gets some PRLs in these places. So this is 4 orders of magnitude. Experimentally, this is what it looks like. Then we went and took a very nonlinear problem. Raman scattering, full nonlinear code, every instability in a pig code. And here's those results. That's a PRL with a very big computer. There was 1,000 spikes, by the way. You didn't ask me. There were 1,000, speckles in those simulations, roughly 10 by 100. 10 lengthwise, 100 sideways, because they're the long same things. This also has 1,000, but in 3D, so it's less dense. But still, 1,000 speckles, which gets you enough statistics. And this is the technology of the field: RPP, SSD, ISI, and this is what stud pulses do: 2 orders of magnitude reduction in a full nonlinear regime, with everything happening, right? With the same rules that we learned by that analytical theory, which gave rise to this field. So there's more examples. I won't bother you with. All right, so let's move on to another instability and do something nonlinear. Well, that was nonlinear, but you didn't see the dynamics. So let me show you the dynamics. So this is a canonical problem called resonance absorption. It's got very nice pieces of physics in it. Each term means something, and it's a nonlinear generalized nonlinear Schrodinger equation with inhomogeneity and driving. Okay. And the game now is to compare what I worked on as a postdoc. Wow. 40 years ago, which is this equation with the right-hand side being turned to 1, this normalized object, to putting in stud pulses. So this will show you how bad it gets, and then I'm going to show you how you can make it better or worse with stud pulses. thus proving that we can control it. And if you want to see the chaotic evolution of this thing, it's a colleague of mine at the time, Olivier Laroche, who did some chaos calculations. So here, let me give you the punchline. The middle one here is S of ZT, the stub pulses, is 1. So it's laser that's on all the time. Okay, I'm going to show you a movie. And well, okay, so this is just the beauty of the model. The reason I'm fawning over this model is because with proper normalization, there's only one knob. And the knob is a nonlinearity knob. Physically, this is a ratio of how big that is compared to what the scale length was here, which now you can see everything is 1. So P, the bigger P is, the more nonlinear you are. You can be more nonlinear by steepening, or you can be more nonlinear by increasing the drive in the right order, 1/3 scaling, whatever. But okay, so P. So as a function of P, let me show you how much worse it gets. So this movie is now going to show you 6 cases of increasing P. So the bad trouble is in this region. And then this is a witness region. And so as you can see, as I increase P from 1.24 when it first becomes non-stationary, any P less than that number, there'll be a fixed form and it'll be like an array function and whatever. So, but as I increase it, it gets very chaotic. In here, the one spike that's being generated is generating solitonic partners with which it's interacting before they slide down the hill. Okay? It's a fully chaotic system. I'll show you the frequency spectrum in a second. So here's some more examples, and the linear case would have looked like that. So if you make P equals 0, it's an analytically solvable problem, not a chaotic problem. All right, next. There's a trick you can use in this problem, which is beautiful. That is that all the stuff was happening in a little region, remember? And the rest were just moving down without interaction. So I can focus in this region, average it. I can do much more sophisticated things, but I can, the least I can do is just average it. Think of it as a temporal signature and say, how can I tame that? And then hope that that's enough to get tame the real thing. I'm just going to show you that that's true, right? But that's a trick. And so, you know, when it's P is 0, then of course there's no time evolution when I average it. And then it's little by little starts getting chaos. So now you're seeing the chaos, right? Not just something going up and down, but the actual temporal complexity. And this is what happens when you make P larger. It gets successively more and more complex. And let me show you that in frequency space. So now you can, if you know anything about chaos, this P value, these frequencies are a hell of a lot more chaotic than that. You see? Chaos, from a frequency point of view, means filling in the frequency. So all sorts of modes are talking to each other, generating new modes, and the whole thing is just filling in. And when it becomes white noise, then you're in a very chaotic region. Okay, so now let's do something. So I'm going to start with something that looks like that and tame it. Okay? And I'm going to make it worse with the wrong stuff pulses. This is showing you how those frequencies got formed. That was the total picture. But this is showing you how, as I said, you know, frequencies mix together and form new frequencies. That's this business. All right, and then there are 3 knobs by which we do our choice of stub pulses. We do the L1 norm, which, how many people here know what L1 norm means? Okay, so I'm going to make a cartoon version of this, and I'm just going to count the peaks. Okay? I mean, just look at the peaks, like as if they're delta functions, and look at their heights. So the sum of those heights is called the L1 norm. The sum of the square of those heights is called the L2 norm. And that's called energy, right? So if I do the sum of the squares of the Fourier modes, it's the Parseval's theorem. That's the same thing as the energy in my original signal. And then I'm going to look at the frequency spread. So this spread is different from that, different than this. So notionally, if I get more and more frequencies coming in, that's more nonlinear, right? So I'm gonna try to contain that and bring this down. That's my goal. And then I can plot, as I vary the stud pulse knobs, the horizontal line is the no stud pulse case. So I'm trying to do better. So I want to make things smaller. Here it's smaller, here it's smaller, here it's smaller. It's no good. You see? So I know where the phase transition is. And now let me prove to you that working off that temporal thing actually gets me the thing to look tame to you. So this is back to projecting that problem's original space-time behavior. And instead of judging it by averaging over time here, just look at how this flows versus. So the one in the middle is the continuous case. The one on the left is much better. The one on the right is much worse. Right? So let's look at that. So focus on how this is evolving versus that. And then look how much worse that one is. So now you know I have control with my techniques of L1, L2, delta omega max to pick stud pulse parameters, the jitter, the duty cycle, the DT on over DT nonlinear. And I know my DT nonlinear by the biggest peak in those frequency plots that I showed you earlier. So it's completely automatable. No human intelligence is involved once it has. Okay. Let's switch gears. I didn't show you this thing kinetically. So I'm going to show you one case of that same problem in an inhomogeneous plasma, now with the whole physics, not that simple model, and without stud pulses, just to show you how bad it gets, because there's more physics kinetically than there is in fluid limit. In the fluid limit, those solitons were interacting. That was the bad news. Here, you can have trapping of particles, and you can have wave breaking. You can throw particles at very high velocities. So let me give you an example of that. And this with stud pulses, those cases, you would tame them. So on the left is the density, and on the right is the distribution function. Okay, so the integral of the right over velocity, over the vertical direction, is the thing on the left, with the gradient taken out. Okay? So you can see those spiky things, but now look what happens in phase space, in velocity space. That's wave breaking, and now you're going to have a train of trapped particles. Okay, and so the job of stud pulse is to try to tame that. Now I'll show you one and final example, which is Raman scattering, and that's these. Remember three-wave interaction? There's the pump, remember, and there's a scatter light wave, and there's the plasma wave, and all the nonlinearities in the plasma wave. It's got extra nonlinearities. The three waves talk to each other through these terms, but on top of it. But on top of that, delay here. I don't know why. All right, so I want to go back. On top of that, on top of these beta naught squared, A naught, A2, A1, A2 terms, there's also A2 squared A2. So it's self-interacting when it gets big enough, right? And so what that does, in the next slide, is look at the nonlinearity that is accrued here. So these are the three waves, the plasma, the scattered light waves going this way, the lasers going that way, the scattered light waves getting amplified, and the plasma waves underneath. You can look at this in frequency space. Those are the three waves. And this is a snapshot near the end of the three waves. That's the plasma wave. The slow nonlinearity of that guy completely screws up renders chaotic the other two waves. And this is the ODE version. The ODE version of that is you drop all the spatial terms. And so what you see as you have three waves is how chaotic they are, or how smoothed out this is going to be as I put stud pulses on. You know, all those odd little geometric things, I just wash over them. And so this is the punchline. So we looked at two instabilities. Actually, we did more than that, but let's just stick to Raman and resonance absorption. I also showed you Bedros. So you have IDE models, ODE models, and PDE models. So you have different levels of fidelity in these models. They do more physics. And you can put stud pulses in any of these models and ask what optimizes one. And so the real key thing of this work is to ask, in this parameter space, if I fix it with ODEs, does that help me with the PDE problem? If I do with PDEs, they help me with the IDE. Conversely, if the IDE problem gets the answer right, how bad would it be with ODEs and PDEs? Is it worth building fidelity? So that's a deep, deep question in machine learning, and we're addressing it for this case. Because there's a lot more than just a 3-knob representation of general stud pulses, right? That was just a trick to begin with. And so you want to do those with your ML model, trained on this data. That's it. Thanks.
Now we have 15 minutes for questions. Any questions from the audience?
I just have a question regarding the whole
Wrong. Yeah.
model. Yes. I was asking why when the laser beam is getting to the whole room,
LEH.
yeah, and the aim to compress the middle part, and you say we want to keep the middle part cold and the beams are going to be really hot and we want the pressure to reach the center first.
No. I didn't explain that correctly because it's not relevant to the laser matter interaction problem. The point of a Hohlraum, Hohlraum in German, which is one of the critical, by the way, thought experiments that Planck did to come up with the Planck radiations. It's called the light trap. Right? Imagine the LH is like almost non-existent. Light that goes into this medium will just rattle around and thermalize. That was Planck's idea of coming up with the Planck's distribution function, and quantum mechanics was born. So in our case, we want the light to go in, nothing to come out, and it to make X-rays on the walls because it's high Z material. The optical photons or the infrared photons or UV photons will go and excite upper levels of gold or lead or depleted uranium and turn them into soft X-rays. Of course, there'll also be hard X-rays, but anyway, let's just simplify this. It'll be soft X-rays, and then you want the soft X-rays to sort of thermalize like a microwave oven inside of these things, come from everywhere, right? The microwaves that are excreted by the equipment in the back is not uniform, but the thing uniformizes them, and that's why the whole chicken gets cooked, right? So if you put the laser directly onto the capsule, the thing in the middle, like in direct drive, you run the risk, so you have to overfill it, so you're throwing away a lot of the laser energy in order for it to be uniform, and it won't be uniform. There'll be always imperfections. In the old days, lasers were much less controllable, so this is a way to take a hit in the beginning. If LPI doesn't happen, though, because when LPI happens, this gets just much worse. Okay, but without LPI, you put the laser in, cooks in a microwave, slowly heats up the whole thing, forgets about its origins because of thermal properties of this X-ray generation and adiabatic movement of the walls, which you need a gas in order to push back. And the punchline is the gas is what causes LPI. So either you can have this gold move in a way that's very difficult to analyze as it, that's a whole story. So, but it's not an LPI story. So that's why I didn't say it. So that's what you wanted to know, is that it's done with X-rays?
Yes.
Yes.
Okay, I have a question. I have two questions from the audience online. So from David Montgomery, what happens if you don't quite cut a speckle in half, or your laser can only partially do that, like cut the entire plasma length in half? Does one still benefit from the STUD pulse?
Stud pulse, yeah, absolutely. Actually, he knows the answer to this, but I'll answer it anyway. Thanks, David. Appreciate it. The answer is the critical cases. Cut in half means not 90%. Okay, so you want maximum help. As I said before, if you cut it to 10%, then you just choke this thing. Nothing is going to happen anyway. Everybody knows that. It's like getting rid of your speckle. But let the speckle sit where it is. If you want to do much better than if it had a chance to have the runway of the whole speckle, the answer is cut it in half. doesn't mean that 60% or 40% doesn't work. It just means that if you calculated all of those cases, you would peak at 50% as to how much you get out of it. And the reason is, that's not obvious. I didn't explain it. The reason is the price you pay of cutting it in half, since remember this is T-pulse fixed and energy fixed, is that I gotta make my intensity higher. Well, intensity higher is not a good thing for LPI. That's another reason why nobody thought of this. Who would think that the right thing to do is increase the intensity and that you'll have a better time, 4 orders of magnitude reduction? The answer is yes, 5 times higher. That was the 20%. So 20%, 5 times higher intensity, and I get 4 orders of magnitude reduction. Because I'm playing this game of how long it takes for it to heal the information by not putting the speckles on top of each other, comparing it to when it's always on top of each other, so that you win. So that's the answer to that. What's the second question?
This is from Robert Kirkwood. Do you envision when this is implemented in inertial fusion energy that there will need to be a number of experiments with the same target and different pulses to generate a data set that can be used by machine learning to optimize the pulse? If so, how many experiments are likely needed to optimize the pulse for a particular target?
Okay, it's almost a good question. The right question, which is very similar to that, is how much can you learn about the plasma? Remember, the real problem is we don't know anything about the plasma when it's complicated, because there's not enough diagnostic, there's not, this varying in time and space. Remember, we're trying to affect it on a picosecond time scale. What measurement are you gonna make? You're gonna make sub-picosecond measurements everywhere at every angle, you know, to learn something about the plasma? Well, you need to know everything about the plasma? No. So a very deep and important thing happens, which you could have asked, but he didn't, is, these are all co-authors of mine, by the way, so sorry, I'm getting the soft questions here. Is that taming the plasma and being able to make it predictable are actually the same thing. So what you're really using the stud pulses for, with this rifling of many, many examples, is to find how tame can it be made at all. And only if it can, it's a information content problem. So okay, so let me give you even a deeper point. In this problem, there's a complexity cap, right? The complexity is in the plasma and it's in the laser. The entire field has worked on trivial lasers, and oh my God, look how complicated the plasma is. Let's get away from that. Okay? Instead of embracing the complexity without knowing what it is and saying, I'm going to transfer it over to the laser. So I'm going to have sophisticated laser space-time evolution to soften up how bad the plasma gets. That's what memory loss means. And then I'll be able to do whatever I want. So that's the reason. It's not how many shots, and it's not on what laser. It's, can I take the complexity? And that, of course, is gradual. Am I trying to solve a problem very far away from where the community is? Not necessarily. To beat them, I don't have to go very far, right? So I can go any amount of distance away from where things are when you're not very good at what you're doing. And what you do is you just make the laser as simple as possible. How simple your laser is, and then have incredible complexity in plasma, or try to hide that. And said, oh, we'll just go to your threshold when nothing is complex. That's not the way to solve the LPI problem. To solve the LPI problem, that's running away from the LPI problem. Einstein has a very famous quote, you know, highly trained professionals solve problems. Geniuses eliminate problems. So the way you want to eliminate the problem is to know how far you can go from the simple limit and still be able to control it by taming it. Right? Now, if you're a mathematician, what that means is that there's a dynamics, and then there's an augmented dynamics with the laser, and the complexity of the augmented dynamics in some parameter regimes is simpler. That's what you're searching for. So there's 2 things that can get you. One, this search is very difficult. And so you have to decide, like Bob asked, is it worth it? My answer is don't be in that regime. There are many regimes. I showed you 3 different levels of complexity, incredibly chaotic things, all of which was getting tamed. So I don't think I have to prove to you that you can go very far, but you know, and by the way, this all gets simpler in more dimensions because things don't get as complex in more dimensions. This is everything talking to each other all the time in 1D. The minute you relax the underlying embedding dimension, then of course things can talk to each other as easily. Okay? So the fact that I can do it in 1D, I can do a lot better in 2 or 3D because the population that's doing the bad stuff is now surrounded by. Yes.
Any technical issue, or you've probably talked with the people who, right up to the master oscillator room. If I now try to take these megajoules of energy and then make this.
It's in the master oscillator. We have patented designs of doing this on this,
But I mean.
which are built at Livermore.
Right, but there's no, I don't know, subtle technical things that don't work well when you actually try to do this, or the real laser.
Of course there are, and they're avoidable. That's why, another way to ask that question is, why did I have the IMAX fixed case? So the way a laser pulse looks like on NIF, I don't know how many of you can see this, and that's a slide I didn't put in, it's there, it's in the patent, the slide, which is taking their 4-shock thing to the foot here. All right, and actually there's 2 cones, right? So there's another one that's a little different. And saying that you got to turn it into this stuff, okay? Right here, one interjection. A laser is an object, big laser, is built to work at damage threshold at its peak intensity. You can, if you know economics 101, that tells you that's got to be true. You're spending all this money to get this energy in, so you just build it just where you can get away with it. Right? There's no margin. And so if I want to make this 2 to 1 higher, there is a problem. First observation, this is 5 nanoseconds, this is 20 nanoseconds. No problem here. That's the first answer to your question. And the need here is infinite, actually, because here is where the beams cross. First. Secondly, this actually increases the frequency conversion efficiency. Frequency conversion has a problem with a pulse like this. It too is optimized to get you most energy at this intensity. The frequency conversion at this intensity, because it's a nonlinear rule, is horrible. All the energy in this part of the pulse is converted, they never talk about it in Livermore, at very, very bad rate in order to get that converted. I solved this problem in my sleep by having stop pulses. It's gone. Here, you make the intensity on the way in this part of the pulse like that, and a bunch of them, conversion efficiency is the same as here, right? You know, so, and the same thing with crossing beams. So anyway, we can talk about that. Once you come here, you don't want to do this because this can break your laser. You build the next laser so it doesn't. But for today's laser, what do? You go to IMAX fixed. So it's always in laser fusion. I didn't give you those slides because I never would have gotten my work. There's a energy versus intensity battle, also known as pressure versus energy, right? So you want to drive this thing at the maximum pressure if you can. Maximum pressure means maximum intensity. LPI gets you much before you can do that. However, you need to have more energy. It's a hydrodynamic instability versus laser plasma instability game, laser fusion. So thanks for allowing me to actually make these old man observations, which have nothing to do with math. So I don't like making observations. Anyway, so what happens is, if the target is thin, you're susceptible to hydrodynamic instabilities. But to drive a thin target, I can use a smaller laser, less energy. If I thicken it so that I don't have hydro, now I need a lot more intensity, now LPI will get me. What's the solution? The solution is, it's a battle. Here, I don't need, so when we get to the thinness of the target, once I go to IMAX fixed, I have to make it twice as long to have the same energy, which means it's got to be thinner for it to get in at the same time. Great. You guys are such experts at polishing your targets, make them half as thick. You see? So that's the game. But that's only here. And this has gotten shorter and shorter and shorter, by the way, with all the homeronomies.
Have you gotten to the point where you could make a proposal to do some first tests of NIF?
Oh, 6 or 7 years ago, yes. This was invented in 2010 after a JSON review where I argued that everything is going to go to pot, which it did. And I thought, well, I was telling him everything's going to be nonlinear, and the system was saying, oh, no, it won't. And I thought, I'll end by telling you how this was invented. So after the Jason review, we wrote the report. I'm like, this is crazy. What I'm saying is true. They're just denying it because it's professional deniers. Every believer in fusion is a professional denier of what's going to get them. That's not surprising. But how can I get them? I'm a chess player. How do I just checkmate them? So, okay, why don't I prove that it will never be linear, that you can't make it linear? Right? That's the premise of my argument about nonlinear things. Let me show them that if you try to make something linear, you can't. And then I invented a way to keep it linear. So by then I forgot about them. I said, okay, this is what we have to do. That's how I know this is what has to be done. If you had, it's a Gedanken experiment, some Maxwell demons in the target. Because remember, we don't know what the target's doing. We don't know when an instability is going to go. It depends on density, temperature, gradients, velocity gradients, intensity, wavelength, plasma evolution, kinetic effects. I have no idea what the plasma is doing. But what if I had a Maxwell demon who told me, hey, things are heating up here? What's the only thing I can do? I showed you earlier, you can try to play with the polarization, and it's completely ineffective in general. The only thing is turn it off. Okay, but now we got to turn it back on because we got to make this thing, keep imploding this thing. So when do I turn it back on? And if I turn it back on and I go to the same place, I'm not going to win. That's going to accumulate things a little slower, but the ratio of the growth rate to the pulse length is thousands or tens of thousands. So this kind of game won't work. I got to scramble my hotspots. Now it'll work because now I can have a lot of damping time, a little bit of growth time. And that's how you get those orders of magnitude. Okay? And so that's the origin of the two pieces of the thing. And by the way, let me give credit where it's due. Gérard Mourou, who has a Nobel Prize for inventing a certain thing in lasers, was just earlier, saying, hey, why don't we use what I call a billion laser march to fusion? So why don't we have fiber lasers, which can maybe do some millijoules, and then we'll have, to get megajoules, we'll need a billion of them, and a billion of them will come and hit the target. I was just inventing stub pulses. I thought, shit, if I had that with stub pulses, everything would be scrambled for free. Okay? So then we have to go back and think of the lasers we have and think how we would scramble. But the scrambling idea came with Mike Campbell asking me, if you put your pulses on Gerard's setup, what would happen? What would happen is everything will be scrambled every time. Right? But that's a crazy idea, having a billion lasers, all controlled, all this, all that. Good luck with that. So now we have techniques that can work at Excimer, we have techniques that can work at Fuse, which are not the kind of lasers they want to build, which are not a billion laser march to laser fusion.
Thank you very much, and let's thank our speaker again.
If any of you want to work on any of this stuff, there's a lot of work to do.